Welcome to lesson 7, graphs of polynomial functions. So in this lesson, we're going to talk about the general characteristics of what polynomials look like when they're graphed. We will identify some things about their graph behavior, including the things that happen on the ends and what's happening around x-intercepts. And then we'll talk about a couple more pieces of information and do the best we can to graph them. It's one thing that's really important to realize is that you won't actually be able to graph these 100% accurately until you are in calculus. And so we'll talk about that as we go through these things. Okay, so we're going to start with just some nice things to know about the graphs of polynomial functions. So polynomial functions are unbroken continuous graphs. So your pencil is never going to pick up and jump from one graph or one spot to another when you're graphing a polynomial. It'll be a smooth, continuous curve. And in fact, it is smooth. It's rounded. All of your curves or turning points are rounded. There's no sharp corners when you graph a polynomial. And so last but not least in this list, the graph of a polynomial function of degree n has at most, and that's important. It doesn't mean it always has. It just the most that it can have would be n minus 1 turning points. So remember what a turning point is. It's like the vertex of a parabola. So if I'm looking at this first picture where the graph switches from increasing to decreasing, that's a turning point. Or from decreasing to increasing, that's another turning point. So this particular graph here, you'll notice it is a continuous curve. It's nice and smooth, rounded corners, no sharp edges. So this is a polynomial graph, and it has 1, 2, 3 turning points. So it could be a degree 4 or higher, because a higher degree could have less turning points than that. But it couldn't be a third degree polynomial because a third degree would have at most 2 turning points. Okay. So I've already kind of identified this one as a polynomial graph. That is definitely going to be one that we would consider a polynomial. I'm looking at this question here. Which of the graphs on the right are graphs of polynomials? And why can't the other graphs be polynomials? So we just talked about why this one would be. What about this one? This is not a polynomial. And the reason is it's got a sharp point. One of the turning points is not a smooth, rounded curve. What about the next one down below? No breaks, no jumps, smooth turning points. This is a graph of a polynomial. Again, notice I have 1, 2 turning points, so it could be a 3-degree, third degree, or higher. And last but not least here, this has the look of a polynomial right until this big jump. So that does not happen in a polynomial. So this has got a break, or you could call it a jump, and that is not a characteristic of a graph of a polynomial. So I think I said in the last lesson that mathematicians call polynomials well-behaved functions, and you can kind of see visually why that is the case. Okay, so I did mention that you're going to need calculus in order to find the exact graph of a polynomial. And the reason is because the precise locations of the max and mins, so this and this, you actually need calculus to figure out exactly where those are. And so we won't be able to do completely accurate graphs of polynomials in this class, but we can determine some aspects with precalculus. It might just be that we go to graph this and we don't quite hit it as low as it needed to go. And so it's a little bit inaccurate in this area, but we still have a general idea of what the graph looks like. Okay, so let's start with intercepts. And what we're going to be talking about specifically are x-intercepts in this section. So graphs do behave differently at various x-intercepts. So sometimes your graph will cross. Let's see if we have a picture of that up here. Perfect. here's a graph, an x-intercept right here, and the graph is just crossing from one side to the other side of the x-axis. That's a common thing that happens. Other times, the graph will touch the horizontal axis and bounce off, which is what's happening right here. You can see that it comes up, it does have an x-intercept, but it doesn't cross to the other side, it bounces back down. Okay. And again, you can see I've got another example for this right here. Suppose we have this graph. This is the graph of this function. This function is written in factored form. So x plus 3, I would expect there to be an x-intercept then at -3, and there is. X minus 2, that I would expect there to be an x-intercept at 2, and x plus 1, so I would expect there to be another one here at -1. And you'll notice that the behavior of the graph, how the graph is acting, shaped, is different at each one of these x-intercepts. So the x-intercept, let's start, we'll go left to right here. We're going to start with this one, the x-intercept -3. That's the solution of the equation. Like if I had set this whole thing equal to 0, right, then we would have broken up each set of factors equal to 0, right? And so the -3 comes from the x plus 3 equals 0 portion of that solving. And that is a what kind of factor? In other words, what's the degree of the x in that factor? It's just 1, right? So it's a linear factor or linear equation, I guess you could say. Either way, it's just x to the first power. So that gives us a hint that the behavior of the graph near that intercept is like that of a line. Linear factor, this is like a line. A line would just go right on through the x-intercept. So let's look at the next one. The x-intercept here at 2, that comes from the solution of which part of this equation? It's up here, the x minus 2 squared equals 0. That's not linear anymore, right? Because it's squared. What do we call things that are the highest power is 2? That would be a quadratic equation or factor, however you want to write it is fine. And so you'll notice that the behavior near that intercept is like it's a vertex of a parabola. It comes down and it bounces back off. So it looks like a parabola because we were solving something that was of a quadratic nature. So last but not least, oh, sorry, I was going to go to the -3, but I see I have a little bit more to say here. So the factor x minus 2 appears twice in the factored form of the polynomial, x minus 2 squared. The number of times that a given factor appears in a polynomial equation is called the multiplicity. So it is a quadratic factor, or we could also say x minus 2 has multiplicity, which is a long word, 2, okay? And x plus 3 has multiplicity 1. So last but not least, we're going to look at the x-intercept -3. Oh, nope, that should not be -3. Sorry about that. That should be 3, right? That we've already done -3. Oh, no, it should be -1. That's what it should be. Let me fix that real fast. Sorry about that. So that should be a -1. That's the last intercept we're looking at. And that's the solution of this part of the equation. X plus 1 cubed equals 0. We look back up here. X plus 1 cubed. There was 3 of them. So it has multiplicity 3. Okay. And what we see in the graph is it does cross, similar to what happens here at -3, but it doesn't do it in a kind of a linear fashion. It's more of a curved fashion. That is similar to the behavior of y equals x to the third, but we're going to see that in the next lesson. So that piece will look more familiar when we look at the y equals x cubed function, but the y equals x cubed function really does just basically do this shape. Okay. So, which is, let's make sure we filled this part in here. So the x-intercept is the solution of this equation, which is a cubic factor or cubic equation. So the behavior of the graph near the intercept is like that of a cubic function. And this 0 has a multiplicity of 3. So we said x minus 2 as multiplicity 2. You could also say that the 0 itself is just 2, has a multiplicity of 2. The 0 of -1 has a multiplicity of 3. Either the factor or the 0. The word multiplicity could apply to either one of those. So the conclusion we're going to draw here is that when we're talking about behavior of the graph at the x-intercepts, here is what we can conclude. The graph of the polynomial will touch the x-axis at zeros with even multiplicities. So if it is a multiplicity of 2, you'll notice it touched it and it came back up, but it didn't cross. Similar to what we saw on this graph here, it came up but did not cross. It touched it. So this 0 has to have a multiplicity of either 2 or 4 or 6. It's an even multiplicity. Okay? That means its factor has a power that's even, 2, 4, etc. And if the graph crosses the x-axis, then that 0 has an odd multiplicity. So again, both of these, here and here, the graph did cross from one side to the other of the x-axis. This had multiplicity 1, and this had multiplicity 3. So the behavior is a little different. It's a little more linear here and cubic here, but it does cross from one side to the other. And what's really important to realize is that the sum of the multiplicities is the degree of the polynomial function, right? So if we were to have multiplied this whole thing out, we would have had 1, 2, 3, 4, 5, 6, x to the 6th as our highest power of x, and that would have been the degree of the polynomial. So I can kind of see in my graph, I have 1, 2, that doesn't really look like a turning point, does it? That's not a turning point because it doesn't switch from going down to going up. It just goes down more. So I have 1, 2, 3 turning points, but it's a 6th degree polynomial because some of these turning points have different behaviors. So that's the first piece of information that we need to know about in terms of polynomials, is looking at the degree or the multiplicity of the factors and the zeros, and then understanding how that contributes to the behavior at that x-intercept.